So today we will be analyzing the physiology of the respiratory system and the exact functions that need to take place during respiration. So the first thing we are going to identify is the main function of the respiratory system, and that is to supply the body with oxygen and get rid of the carbon dioxide that is built up within the body. And to do this, 4 events have to happen within respiration, and those 4 events are found right here. The first event is pulmonary ventilation, which is just moving air into and out of the lungs, and it's also the act of breathing. Next is external respiration, which is the gas exchange between the lungs and the blood. The third step is the respiratory gas transport, which is the transport of oxygen and carbon dioxide between the lungs and the tissues. And then finally, we have internal respiration, which is the gas exchange between the systemic blood vessels, which I will label BV, and the tissues. Now, just for your reference, whenever we say gas exchange, we're always talking about oxygen and carbon dioxide. So the first step is pulmonary ventilation, but before I explain this slide, I want to talk about the 2 zones within the respiratory system, and those are the respiratory zones and the conducting zones. The conducting zones are these rigid pathways. And they're almost like conduits, so the air is able to reach these sites of the gas exchanges. And these respiratory structures include the nose, the nasal cavity, the pharynx, and the trachea. And these air passages undergo 23 orders of branching in the lungs, so that it increases the cross-sectional area for flow. And then for the respiratory zones, which I will explain down here, are the exact sites for gas exchanges. And these consist of the bronchioles, the alveolar ducts, and approximately 300 million alveoli. And these respiratory zones account for most of the lungs' volume and provide the tremendous surface area for the gas exchange. So I just wanted everybody to know these 2 different types of zones so that when we reference them later in the PowerPoint and in the chapter, we all understand what those are. So now back to the PowerPoint with pulmonary ventilation. Ventilation is a mechanical process, and it's exactly what it sounds like. It is breathing. It is the direct inhalation of air, and we look at the changes of volume and pressure within the thoracic cavity. And if you think back to your physics days, you may have heard something as Boyle's law. And all Boyle's law is, it shows the inverse relationship between volume and pressure with this equation of P1 is times V1 is equal to the pressure and volume of the second chamber. And the indirect relationship comes in where if pressure increases, then the volume will decrease. And this goes for the other side, where we'll have the same pattern where if pressure increases, the volume will decrease. And it's inversely related, so if it were true for volume to increase, the pressure would decrease, because this is how gases behave. Their ability to completely fill the area or the volume in which it is occupying allows for this inverse relationship. And specifically for the lungs, it allows for the lungs to equalize pressure to atmospheric pressure. And with pulmonary ventilation, there are these two subphases, inspiration and expiration. All right, so let's talk about the first event in pulmonary ventilation, and that would be inspiration. And inspiration is the act of bringing air into the lungs. And when we bring air into the lungs, the diaphragm and the intercostal muscles will contract, and this will ultimately increase the size of the thoracic cavity. So if we already know that the volume is going to be increased, we know that there is going to be a decrease in pressure due to Boyle's law, in which we investigated in the previous slide. And then, because the lungs and the diaphragm need to move as one cohesive unit, the lungs are physically adhered to the lining of the thoracic cavity, and there's this surface tension due to this fluid between the two pleurae, the visceral and the parietal pleurae. And therefore the lungs can expand as the thoracic cavity expands. And this adhesion is due to the interpleural fluid cohesiveness, where the polarity of the water attracts the wet surfaces, and the thoracic wall and the lungs are able to move as one cohesive unit. So as inspiration increases, the intrapulmonary volume will increase, as we described before, and the pressure will decrease, so we have this vacuum. And this allows the air to move into the lungs until the pressure inside of the lungs becomes equal to atmospheric pressure. Now, pressure in regard to anatomy and physiology is always labeled as millimeters of mercury. And 1 atm is equal to 760 millimeters of mercury. And so the outside of the body is 1 atm at 760, and we're always referencing to the change of pressure relative to the pressure outside of the body. So the air that is acting upon us outside. So in this diagram, we can see how the thoracic cavity and the lungs are able to expand and decrease their size. So in inhalation, on the right hand side over here, we see that the lungs are able to expand and the diaphragm sinks, while in exhalation, the diaphragm is able to rise and the lungs recoil and return back to their resting size. So the second step of expiration is supposed to be a passive process, meaning that no more force is needed to move air out of the lungs, and this should be a normal process for healthy people. So expiration, no more force is needed to remove air from the body. And that's because of the natural elasticity of the lungs, and with the help of the relaxation of the diaphragm with the intercostal muscles. So if we know that the volume is going to decrease, we know that the pressure is going to increase because the gas molecules have a smaller space to occupy. And so the gas molecules are going to clump together and act upon each other to create the increased pressure. And then the air is going to rush out of the lungs until pressure is equalized to about the magic number of 760 millimeters of mercury. So in expiration, the whole entire thoracic cavity relaxes, and due to elasticity and gravity, everything and the volume is going to decrease. And then in one respiratory cycle, you are going to get what's called the tidal volume, which we will talk about in just a second. And this diagram just shows how the anterior and posterior positions of the thoracic cavity move as we expire and complete one respiratory cycle. So another important pressure that we need to know about is the intrapulmonary pressure, along with the intrapleural pressure. And the intrapleural pressure is the pressure within the pleural cavity that adheres to the lungs in the thoracic cavity. And it is always a negative pressure, because if it is a positive pressure, it'll cause the lungs to collapse. And so we need this gradient differential to ensure that our lungs stay intact and are able to carry out respiration properly. However, there's this fine balance where if we have too much air in this pleural space, it'll disrupt the fluid within the pleurae and the bonds will break. And then again, if the bonds are broken, the lungs may not expand with the thoracic cage, leading to a collapsed lung. So as you can see here in this image, we have our visceral pleurae represented by this blue line right here, and that which helps adhere to the lung, in addition with this pleural space with the parietal pleurae all encompassing the lung. And so within this area, we have to have a negative pressure. So back to more respiratory volumes and capacity. When we talk normally and complete a respiratory cycle of inspiration and expiration during pulmonary ventilation, we normally take in about 500 milliliters of air, and this is called our tidal volume. And we complete a respiratory cycle within one tidal volume. However, our lungs have a much larger capacity than just 500 milliliters of air. So we can actually take in more, and we can force ourselves to breathe in more, and this is called our inspiratory reserve volume, which is significantly greater at 21 to 3,200 milliliters. And if you think about a doctor's visit, they have you take huge deep breaths in and out so they're able to listen to your respiratory functions. And conversely, if we can inhale significantly more, we can exhale significantly more. However, our exhalation is limited to only 1,200 milliliters due to residual volumes and dead space that are found within our lungs. So there's always about 1,200 milliliters of air that is within our lungs at all times, so that we can have a pressure gradient. And this pressure gradient allows air to always move back and forth and have oxygen and CO2 be filtered in our lungs. And so it also ensures that we have the gas exchange when we aren't actively breathing. Now may sound a little funny because breathing is an involuntary response, but perhaps when our breathing is slowed, such as during sleep, so that we always have that gas exchange. And then the total amount of air that we can breathe in is called our vital capacity. And for a healthy adult, that is about 4,800 milliliters. And we were able to find our vital capacity by adding up our tidal volume, our inspiration reserve volume, our ERV, and that will equal our vital capacity. Now, going back to our conducting zones, and some of this air will never reach the respiratory zone or the places where gas exchange happens. And this is called your dead space volume, which may vary among individuals, but averages about to be 150 milliliters. And we can measure our respiratory capacities by using an instrument called a spirometer. And we're able to evaluate if there's any respiratory function loss and how much flow there is within a respiratory system. And we can calculate flow by using this little equation of flow is equal to delta P over R, where delta just means the change of pressure over resistance. And the resistance could be a physical factor such as friction or a non-elastic source. And our elasticity of the lung can be impacted by disease such as cystic fibrosis or asthma, or environmental factors such as smoking. And then we want to make sure with this formula we can identify the compliance or the ability to stretch the lungs when they're induced by pressure. So right here is an image of a spirometer, and the patient blows into this mouthpiece right here. And the physician can use this sliding piece here to measure how much volume he would like the patient to reach. However, there are some constraints because we want to always assess the tidal volume at which a patient can breathe. And so if they blow too hard, they will actually move this smaller yellow piece into this harder area, or this frowny face area. But if they blow too little, they will not be blowing hard enough and have this other frowny face. So they want to have this happy medium in through here where the happy face is located. And they want the bottom of this light plastic piece to reach wherever the doctor has set that sliding piece. So going back to when you're at the doctor's office and they ask you to breathe in heavily and exhale heavily, they're actually listening for the sounds. And the two sounds they're looking for are your bronchial sounds, or the aspects or the larger aspects of your respiratory system, such as your bronchi or your trachea. And this will be a loud whooshing sound when you auscultate with a stethoscope, and auscultate just means to listen. However, for the vesicular breathing sounds, we're listening for these smaller aspects, such as your alveoli and other air sacs within your lungs. And this will kind of sound like a light breeze. Again, they're smaller so that dramatic rushing of air will not be heard when listening for this breath sound. So we're going to look at some non-respiratory gas movement. And typically these non-respiratory gas movements are going to occur out of reflex, or maybe out of emotion. And you can guess which one is which. So a reflex might be a cough. It could be a sneeze. Crying could actually fall into both because you may have some dust particles within your eye, but typically it's associated with an emotion. A yawn would be a reflex to try to expand your lung when you are not actively breathing. A hiccup is certainly a reflex or a stimulus within the diaphragm to expel additional air. And then a laugh would also be an emotion where you are rapidly opening and rushing air into your thoracic cavity. So the third step in respiration is external respiration, and this is the gas exchange between the body and the exterior, which occurs in the lungs. So the air that was inspired when we use pulmonary ventilation, and it goes directly to the lungs. And the alveoli are rich in oxygen, while the pulmonary capillaries are rich in carbon dioxide, and that makes sense as this is where the pulmonary capillaries are able to convert the oxygen into the carbon dioxide. And the respiratory gases simply diffuse to areas of lower concentration. If you remember from perhaps 10th grade biology, diffusion is the act of moving from higher concentration to lower concentration. And this is a passive route because nothing else is needed besides the movement of the gases. So continuing on, we have the gas exchanges between the blood, lungs, and the tissues. And we have a couple more gas laws that we need to analyze. And the first one is Dalton's law of partial pressure. And all Dalton's law is concerned about is the percent of gas that's directly proportional to the partial pressure. So as we know, we do not breathe in pure oxygen. We breathe in many other gases, such as a little bit of nitrogen, perhaps maybe a little bit of helium, but mostly oxygen as the diatomic molecule. And so we need to figure out the millimeters in mercury for all of those partial pressures of the different gases. And we can use Dalton's law by taking the percentage of the gas and the total pressure of air to find the partial pressure of oxygen in millimeters per mercury. So the air we breathe is typically about 20.9% oxygen. And we can take this percentage of 20.9 and multiply that by 760 millimeters of mercury. And that works out to be about 159 millimeters of mercury. The next gas law we're going to look at is Henry's law. And Henry's law is just concerned with solubility, the ability of the gas to be soluble within a liquid, more specifically blood, as we are concerned about in anatomy and physiology. And the amount of gas that will dissolve in a liquid also depends upon its solubility. So the various gases in air have different solubilities, with CO2 being the most soluble, and oxygen is about 1/20th as soluble, with nitrogen being practically insoluble within plasma. So when we know the solubility of the gases within our blood, we are able to make more accurate decisions on the respiration function of a patient. So the external respiration is based on three very important factors, and that will be the partial pressure gradients and gas solubilities. And so we know that gases have to diffuse from high to low partial pressure, and this occurs between the lung and the blood, and also the blood and the tissues. And we can use Fick's law of diffusion to find the rate of diffusion with this formula of A times D times the difference in partial pressures between the 1 and 2 gases, all over T, which is the thickness of the tissue, where A is the tissue area and D represents the diffusion coefficient of a gas, which is typically a given constant. And with the formulas such as Boyle's, Henry's, and Dalton, we can evaluate the partial pressure and the gradients and the gas solubilities. Next, we have the ventilation perfusion coupling, and that just describes the size or the vasodilation or the vasoconstriction of the blood capillaries. And so when we have vasodilation, you are going to have a increase of oxygen with a decrease in CO2, so that we have maximum surface area for the capillaries to expand. And under vasoconstriction, we're actually going to have increase in CO2 and a decrease in O2. And then finally, we have the thickness and surface area of the respiratory membranes. And typically, the respiratory membranes are about 0.5 to 1 micrometers in thickness. And they are this small because it allows for the maximum efficiency for gas exchange. Males have more surface area with about 60 square meters, which is about 40 times of the surface area of the skin, and so which is a lot larger than our own skin. We also have the air-blood barrier that's composed of the alveolar and capillary walls. And the alveolar walls are a single layer of type 1 epithelial cells. And here's an image of an alveoli where the oxygen depleted or CO2 rich blood comes back into the alveoli to become oxygenated and return to the systemic body. And here is a more microscopic image of the oxygen leaving the red blood cells or the erythrocytes to become reoxygenated within the alveoli. Finally, we have respiratory gas transport, and which allows for the gases to be carried in the blood and shuttled to the tissue cells of the body. And oxygen is carried in two ways. It is carried on this molecule called hemoglobin. And hemoglobin is able to create oxyhemoglobin. And how that happens is that oxyhemoglobin forms when O2 molecules bind to hemoglobin. And so oxyhemoglobin refers to when oxygen is bound, and deoxyhemoglobin means to when O2 is not bound to hemoglobin. And then there's only about a small amount of oxygen that is just free floating within the plasma because hemoglobin has this high affinity for oxygen. And then carbon dioxide is carried in three ways. It's carried in the blood in the form as a bicarbonate ion, which is a part of the blood buffer system to maintain normal pH. And some CO2 is carried on hemoglobin, but it doesn't compete with the oxygen. And again, just like oxygen, there's a very small amount of CO2 within the plasma. So the oxygen transport, there are 4 iron-containing hemes that are on hemoglobin that are responsible for carrying the majority of oxygen, about 98.5%. And then when O2 binds or releases to hemoglobin, the affinity of hemoglobin for oxygen changes. Either O2 is going to bind quicker if it finds a hemoglobin that is able to do that, or if a hemoglobin molecule is already saturated with oxygen, it's going to try to let go of them to make room for more. And the rate at which hemoglobin binds or releases depends on these following circumstances, these 5. And that could be the partial pressure of oxygen, the temperature, the pH of the blood, which a typical range for blood pH is about 7.4. And we typically don't want anything other than that because 7 is about neutral. There's also a partial pressure of carbon dioxide and the amount of BPGs that are found. So the lack of oxygen has a great impact on our body, and the lack of oxygen is called hypoxia. And when you're at the doctor's office, they put this little infrared sensor on your finger, and we typically want to have an oxygen saturation of anywhere above 98%. That means all of the hemes in our blood are binding to oxygen and our body is getting enough oxygen. However, when our O2 sats fall below 75%, this is when a person could be classified into these different types of hypoxia. And depending on the condition or what is being affected, you get these different titles of hypoxia. And I won't bore you to death by reading these yourselves because you can do that. But go through and take some time and look at the definitions of the different types of hypoxia. And the last step in respiration is the internal respiration, or the gas exchange that takes place within the body, and that happens at the cells, at the cellular level. And so the gas exchange that happens, O2 wants to move into the cells while the CO2 moves into the blood to make the carbonic acid, which then turns into this bicarbonate ion. And as I mentioned before, bicarbonate helps with the blood buffer system. To maintain the 7.4 pH of the blood. And that wraps it up for today's lesson.